All right, recorded. Recorded is rolling. Welcome to Tuesday, September 5th, so beginning of a new week. Yesterday was Labor Day. A bunch of you guys just turned in your linear motion puzzles. Thank you for doing that. Since you guys are AP, that's these college physics puzzles right here. Just the ones that I circled. Remember, I circled, I think, about 10 puzzles for you guys. Okay? If you wanted to do more of those, then, well, there were definitely more opportunities there, but you turn in the circle ones, you're all good on that front. Oh, I did also give you guys this page with the boxy looking problems on it. There's 10 different scenarios. Now this really was for my honor students, but if you did this one too, then I'll put in some extra credit points for you guys. Okay? On the back side were some conceptual questions. I think we did a fast version of a Kahoot with those questions. All right, so that was last week's stuff, linear motion stuff. All right, we got coming up. So you guys got your, hold on. Yeah, you guys got your planners out, right? You guys got planners out? So here's three due dates coming up, 3 due dates. Okay, so this Thursday, before you come to school, or at least by the time you get to class, have AP Classroom Unit 1, multiple choice questions done. There's a progress check. Unit 1, multiple choice. I think there's 16 questions. I checked over the weekend. Some of you guys have already finished these. Now, some of these are projectile questions, but I think by the end of class today, after I give you guys the first projectile notes, you'll know enough about projectiles to be able to answer all these questions, I think, right? So have that done by Thursday, because my plan is on Thursday to open those questions up, see how you guys did, go through like the most missed questions, that sort of thing, okay? So AP Classroom, right? Then there's some new stuff on your desk. So one new thing on your desk is this half-page linear motion take-home quiz. Let's have this due this Friday, so you guys got a few days. Right? There's some graph questions. There's some other calculation type questions. Ooh, we got a graph with a couple multiple choice on it. There's some solved in terms of variables. Many different versions of this. I think again, there's about like 10 different versions floating around. But here you go. So linear motion take-home quiz due Friday. All right. Then you guys have also a couple new pages with projectile questions in 2-dimensional motion. Okay. So what do you guys got? So the main thing for you guys is chapter 3 in your book pretty closely corresponds to what we're doing this week, projectiles. Now, chapter 3 in the college physics textbook covers more broadly just 2-dimensional motion. So there are a bunch of projectile questions. Just like with linear motion, I went through and I circled a bunch of them. Now, all of the ones I circled, I think I circled like 7 different questions, are projectiles, except for there's one that involves like a stubborn mule being pulled, number 20. Right? That's really more of a Unit 2 question by AP's book. So that's a good bridge to what we're doing next. I'd like to find a good time this week to walk you guys through that one. But of course, you guys do have the solutions, because I did post the solutions to all these. But just like with linear motion, right, the correct way to use the solutions is make sure that you can do them yourselves. Right? If you really get stuck, then you can check the solutions. But still make sure that you can solve everything just from a blank piece of paper. Okay? You guys got that? So all the ones I circled here, let's have these due on Monday. So you guys gotta find a way to do those. And then also, like with linear motion, I gave you guys the honors version of the homework. There's a bunch of projectile questions here and a bunch of conceptual questions on the back. So if you guys do solve these, there's 6 different projectile scenarios. So if you solve those and turn them in, then I'll give you guys a extra report to the grade book too. Okay. All right, so you guys good with what's due, whatnot? You guys got all this in your planner? You know, a bunch of things there. Okay.
What do you want us to do with projectile motion?
You know what? There is the end of the first interim, I think is the 15th, I think it is. So yeah, if you turn it in, I guess about the same time, right? So like Monday, Tuesday, Wednesday, somewhere there. If I can get in the grade book for the interim, right? Show up on your interim. Okay. Oh, and it looks like these are the ones that I circled. The 11th. Oh, okay. So that is Monday. Huh. All right. Maybe they're releasing your. Okay. Yeah. So the 11th. That could be right, actually. All right. All right. So before I get going on projectile stuff, there's a lot of fun stuff going on around the school. So I stapled it all in this packet here. Let's take a look. Club Rush will be Friday 9/8. Ooh, that's a few days from now. During all 3 lunches, tables will be set up with flyer. Highly encouraged to join any of these clubs. So long list of club opportunities. Let's look through them. Academic team, beta club, book club, chess, dental club, digital media, Dungeons and Dragons, environmental club, fashion club, FCCLA cooking club, future Board of Future Educators of America, French club, Hawk Buddies, Hawk Nation, Hawk Robotics Wingspan, Hawks for Humanity, Key Club, Letters to Strangers, Mock Trial, New Alpha Theta, National English Honor Society, National Honor Society, Odyssey of the Mind, Sources of Strength, Spanish Club, Spanish Honor Society, Tumo, Viera Academic Spanish Club, Viera Fishing Club. If any of these look interesting to you, yeah, that's more opportunities to enrich your high school experience. Here's, I think, a very similar list of clubs, just what teachers are sponsoring them, on what days and what rooms they have. Here, let's see any details on that. Let me know. I've got it right here. Good morning. Below is a schedule for math tutoring this year. Please feel free to share. So maybe you need help in math, or maybe since you guys are AP students, I bet a lot of you guys could probably be math tutors, right? I know that's one thing that got me started eventually on this career path was tutoring. Right? I told you guys a few times before, one of the best ways you can ever learn a subject is to help other people, right? So they come to you with questions like, oh yeah, right? So I think it's fun. So here's math tutoring, and a lot of math goes hand in hand with physics too. So maybe things that you learn in here, questions you have in here, you might get a crossover perspective. It's got Algebra 1, Monroe, Geometry, got Sheratat, Rowe, Miller, Monroe, Statistics, Sheratat, Pre-Calc, Keen and Rowe, Calculus, Bentley, all. O'Boyle, Walker, Mu Alpha Theta. There you go. It's like mostly Tuesday, Thursday. There's a Wednesday and a Friday thrown there. So there you go. We got Mathnasium, open house. So this is off campus. I don't know, this show up on email sometime. 9/9, I think it's a Saturday. That looks interesting to you. Maybe that's a service you could access. I think you have to pay for that one. Or they might, I think I've heard in the past they're hire students sometimes. So might be able to get a job there. Maybe sometimes help elementary school students or something. Do you love math? Mu Alpha Theta. Ooh, I think I shared this to you guys before. So Mu Alpha Theta, these room numbers 3123, 3120. They're offering a tutoring program. There's 2 sides to that coin. You could get help or you could get help. Right? And ooh, this I think I promoted before too, with Miss Barnhill, the Clash of the Clubs lip sync battle. So she's a theater teacher. I know a few months ago she organized a talent show. I had a club back in the day that they got a lot of good out of prepping for that, and it was really well organized event. So that looks interesting to you. I got a bunch of these sheets printed out. It's got a form on one side you can fill out, like an entry form, and there's a bunch of rules printed on the opposite side. There you go. Anything like that looks interesting to you? Fun opportunities around the school. All right, you guys ready for a projectile motion? Projectiles? All right, got notes out, all ready to go. All right, switch my screen over here. All right, let's watch. Hey, where's? Okay, hold on, let me pause this. All right, we're back. All right, so I've got this animation. See, there's a cannon. It's gonna blast a cannonball. Right now, you guys see that orange vector right there? That orange vector. Now, since the cannon has already left the cannon barrel, right? So there's no longer a force from the blast on it. Right? What kind of vector do you think that represents? Maybe a velocity vector? Do you guys think velocity? Okay. All right. Now, if you knew, suppose you knew the blast speed of the cannon, and you also knew the angle that you blasted it at. Do you think it might be determinable, for example, like where the cannonball lands, like how far downrange? You probably saw that, right? I mean, you'd also have to know the gravity of the planet that you're on, right? Let's say you know all those things. You know the blast speed of the cannon, you know the angle you ramp it up to, and you know the gravity field of the planet. But there's some determinable location that it lands at, right? Or maybe you want to solve for that. And you want to know, like, hey, what angle do I have to turn the cannon so I can hit the target, kind of deal? Okay? So how would you figure that out? Okay. Well, the way we're going to do this in projectiles is there's actually no new equations from the last couple of weeks. Right? You guys remember those 3 kinematic formulas? Right? So it's the same ones. Right? So there's nothing new. except that we're just going to be juggling two different dimensions. So the way we're going to do this is we're going to break this velocity vector into components. We're going to say, well, that cannonball is partly going upish and it's partly going across the field. Right, you guys see that? You see that? Right. Now, the only difference I would draw it on the notes from the animation is I would connect these two component vectors tip to tail. So I might take that green one, slide it over, connect it tip to tail with the red, make a nice little right triangle. Ooh, that could be a nice little right triangle there. Right? You guys see that? Right. Now let's watch this cannonball in flight. Okay, so there it goes, right? Okay. Now, what shape path do you, oh yeah, go ahead.
Well, it's that one, and also when all of it overlaps and you can't see the red or the green vectors anymore, would that be it at west?
Ooh, yeah, think about that too, right? Yeah, so you're right. So it does follow parabola motion, right? And you're asking like right there, right? Guys, the cannonball when it's right there, let's see, is it at its maximum height, right? Right at that point? Yeah, that would be at its maximum height. Would you say that the cannonball was at rest? Or is it a motion? It's a motion. It has all what kind of motion? All horizontal, right? All for one instant. So yeah, it's on the move. It's on the move really fast relative to the ground, but it's all horizontal just for that instant. So you could say, if you look at its vertical component of velocity, its vertical velocity would be 0 at that moment, as if you had thrown, say, a cannonball straight up, right? Then it would have 0 velocity right at the top, right? All right. And that actually gets to maybe the analysis that we're going to do on this thing, right? Is go back to the beginning, right? Let's focus on each one of those components because those components are a lot easier to make sense of them. See, it's an orange total velocity vector is constantly changing, right? It's shrinking on the way up and it's growing on the way down. But in terms of components, let's look at just the red one. You guys see the red one says v sub x, v sub x. All right, let's focus on that guy for a bit. Right, v sub x. Hey, what's that red one doing the entire way across? Not changing, right? So it's just constant velocity all the way across. Because think about it, well, which way is the only way that gravity ever pulls? Down, which is like a vertical direction, right? And we've been ignoring air drag all along. We'll continue to do that. And if that's true, there's no horizontal force on it, which means there's no horizontal acceleration, which means there's no horizontal change of velocity. That's it. So if you were like way up here in a blip, looking down on this whole situation, then you would see the cannonball go across the field. It would look pretty much constant speed across the field because you would just be detecting like that red component, right? Yes, yeah. Right. Now let's switch over to the green component. The green, you guys ready for the green component? All right. Ooh, that green component is definitely changing. Is that green component changing at a constant rate? Yes, it is. In fact, you guys know a number. At what rate does that green component change? 10 meters per second squared. Exactly. That's to say that every second it changes by 10 meters per second, right? 10 meters per second per passing second. So let's say, for example, that right when it leaves the cannon barrel, it's going strictly up at 20 meters per second. How fast is it going after 1 second? Strictly up. Yeah, so it loses 10. So now it's down to 10, right? 20 minus 10 would give you 10, right? Then after 1 more second, how fast is it going strictly up? 0, right? So that's 0 vertical velocity. Right? Then 1 second later, how fast is it traveling strictly vertically? There, right, yeah, 10 meters per second down, right? Yeah, and if you call gravity the negative direction, you're right, that would be negative 10 meters per second. And then after 1 more second, now it's, yeah, 20 meters per second in the down direction, right? Okay, so in terms of components, this isn't actually that bad, right? Because the horizontal just doesn't change the entire way across, and the vertical one changes by 10 meters per second per second, right? Then if you put it all together, ooh, guys, whose theorem can you use to put it all together? Maybe old Greek guy? Pythagoras. Pythagorean theorem. Can you go the red squared plus the green squared, take the square root, and you get the magnitude of the orange, right? That's the Pythagorean theorem. You guys can do that, right? You guys do that? All right. Let's watch a few Paul Hewitts. We're going to backtrack a little bit and get a little bit of review on vectors. Okay. No, the only difference between what I would do and what he did, I would connect these two vectors tip to tail. So I would take this wind vector and slide it down and connect it tip to tail with the plane vector, right? So here's 100 kilometers an hour. That's the plane relative to the surrounding air, right? The plane engines can push against the air so fast, right? That's this guy. Here's the air relative to the ground, right? Connect those tip to tail. That gives you this resultant. You guys remember resultant vector, right? And that's the plane relative to the ground. So plane relative to the air plus air relative to the ground gives you the plane relative to the ground. Okay, so that 80 take away 20 gives you, or sorry, 100 take away 20 gives you 80. All right. There you go. Let's go 2 dimensions. Oh, hey. Oh, slow down, Paul. Let's try it again. All right, let's try a different player. Open with Windows Media Player. Recommended settings, I guess. Is this gonna play? What's going on here? Ooh, all right. Now, again, I'll do things a little bit different in class. I would connect those two tip to tail. So I might take the wind vector, connect it tip to tail right up here, right? Make it, a right triangle. You guys would see a right triangle going on, right? So the plane relative to the surrounding air can go 100 kilometers an hour. So, and the plane's pointed straight north, right? The wind, there's a crosswind blowing straight east. So it's like that entire air mass is moving 100 kilometers per hour to the east. Right? So do you guys see the resultant right here? Tells you like what the plane is doing relative to the ground, right? Now, there's two parts to velocity, right? Magnitude and direction, like speed and direction in this case, right? Who can tell me what is the speed of the plane relative to the ground? Everybody figure that out? This 100 kilometers an hour, this 100 kilometers an hour, right? So there's some guy on the ground and he points a radar gun at the plane, right? Or if you like, the story of the plane's shadow moves across the ground, right? How fast the plane's shadow moved across the ground. All right, who's got it now? All right, what you got, Steve?
141.
Yeah, 141 meters per second. There you go. All right, and you got that by using Pythagorean theorem, right? You just go 100 squared plus 100 squared, take the square root, gives you 141 meters per second. Or sorry, kilometers per hour, whatever unit we're in. I guess kilometers per hour, right? So Pythagorean theorem, right? I see a nice juicy right triangle right here. 100 squared plus 100 squared, right? Then what is that, like 20,000? Then take the square root. So like 141, right? Right. How about this angle right here? What is this angle? What direction is the plane going? 45 degrees east to north, right? This would have to be 45 degrees east to north, right? No, this is a pretty simple triangle. The two legs are the same. It's a 45, 45, 90 triangle, right? What if it was like any other shape? Like, what if the plane was flying 100 kilometers per hour straight north and the crosswind was like 63 kilometers per hour straight east? Like, you're just some funky number, right? In general, how would you get this angle? Inverse tan. You guys remember inverse tan? You guys remember how you extract it? It's that poster up there says vector components. It's the very bottom of that poster. So how do you extract an angle from sides? You do some kind of inverse trig function. If you're playing off the two legs of the triangle, it is inverse tan of opposite over adjacent. So you can do like inverse tan of 63 over 100, and then get that angle right there. How many degrees east or north? You guys got that? All right, there's vectors review. Let's check out projectile. Okay. We gotta play this. There we go. Ooh, all right, so there's the question. Let me give you guys 3 multiple choice options, and I'm gonna see show of hands. Okay. So remember, he's gonna release it at the top. He hits, bam, hits the switch. And then the one on the right side of the screen flies straight up horizontal, goes into like a parabola type path and hits the table way off screen. Okay. And the one on the left side of the screen goes pretty much straight down. Bam, it's gonna hit the table like right at the edge right there. Okay. So, and they're released at the same time, right? So which one hits the tabletop first? Option A is maybe the one that goes straight down. Bam, maybe that one hits the tabletop first. Option B is, well, maybe the one that was kicked out horizontal. Goes like flies way off screen. Bam, maybe that one hits the tabletop first. Option C is, well, maybe they tie or get pretty close to tie. How many guys, here, show of hands, how many guys think the one that goes straight down gonna hit the tabletop first? Straight down. Anybody say that? Ooh, nobody say that? Okay. Who thinks of the one that goes straight out hits the tabletop first? Who thinks it's gonna tie? Who thinks it's gonna tie? Oh, is that everybody? Is that everybody? Man, why do I even teach? They did hit the tabletop at the same time, right? Because they have the exact same vertical components of velocity. Now they're doing entirely different things horizontally, right? But they got the exact same things vertically. Yeah, so if you stand on top of a cliff and you drop a ball, and at the exact same time you throw a ball horizontally, which one hits the valley first? Same time. Yeah, right. They're gonna tie, right? Because they right. So like second for second, they have the exact same vertical motion. There you go. Okay, let's do one more. Oh yeah, it's kind of neat. Oh, look at that. He's got a bunch of right triangles drawn. Right. You know, I like to draw these in terms of right triangles. He drew it the same way I would, pretty much, right? So see, we blast this cannonball, it's slowing down on the way up, it's speeding up on the way down. Right? At the very top, it's going strictly horizontally, just for like one tiny instant. Right? Right? But then if you break each of those velocities into component vectors, look, side up, side up, side up, side down, side up, right? You guys see it? Right? You guys see the horizontal component is not changing. Yeah, that was like that animation we were just looking at, right? Right? Is that? Let's throw some numbers here. Suppose that right at the blast point, it's blasted at such a speed, at such an angle, such that it's going strictly upward at 30 meters per second. You guys got that? 30 meters per second? How fast strictly upward after 1 second? Like how much does it change every second vertically? Yeah, 10 meters per second every second. So now we're down to 20 meters per second. Then 1 second later, how fast strictly upward? Now we're down to 10 meters per second, and then at the very top, 0 meters per second vertically, right? Right. Then if you combine that with the horizontal, maybe it's going like 12 meters per second, 12 meters per second, 12 meters per second, 12 meters per second. You can put it all back together with like Pythagorean theorem to get the total speed, or you could do some like sine and cosine stuff to like figure out angles. Okay, you guys got all that? All right, let's switch back over here. All right. Oh, I have a few new posters for you guys. But no, this is an old poster, but you guys are probably memorizing these three equations, right? I do highly recommend, right? So same ones where we've been using the last couple weeks, we're going to continue using this week, right? So nothing new. I might modify these a little bit because we do have two different directions going on. So X has a general displacement value. Maybe I'll call it like Y for like a height change, or maybe H, right? You might see, right? You might see different characters here, maybe a D sometimes. Right, this V naught. Now, if we're talking about an accelerating situation, if it is accelerating, then we're only talking about the vertical situation. So I might tag onto that subscript. I might call it V naught Y, like initial velocity in the Y direction. And if we're talking about horizontally speaking, then this acceleration is 0. So we're now just back to X equals VT. And maybe that subscript, you don't even need a subscript, you can call it V sub X, like speed in the X direction, maybe something like that. All right, so that's an old one. All right, let's find the new ones here. All right, let's go to the edge of a cliff and fire a cannon. By the way, tomorrow I'll have you guys outside for a projectile lab. Ooh, look at that, tomorrow, projectile lab. It's going to be really similar to that setup. Actually, that is the setup right there. We're going to go out to the balcony, start blasting some cannonballs. Tell everyone, get out of the way, we've got physics going on. And the question tomorrow is going to be, what is the blast speed of the launcher? Okay? And so let's get big picture idea of what's going on here. Then I'll show you guys the launcher and kind of how this works. Okay? So we're going to blast this cannonball. Now, you guys notice how this cannon is aimed straight horizontal? Straight horizontal. Okay. This is a really classic setup. If you aimed it up at like a 30-degree angle, probably could solve this. It would just be more complicated, right? It'd be extra steps. Bam, just straight horizontal. Because what's nice about horizontal is, well, this is a parabola right here, right? You guys see the parabola shape? Right? Is this the vertex of the parabola right there? That's vertex. Okay? And what is the initial velocity vertical? What is the initial vertical velocity? 0, right? Only if you aim it horizontally. Right? Now, if you aim it that way, it's got some initial vertical velocity that's not 0, or that way for that matter, if you aim it straight down. Right? But if you aim it straight sideways, then could you drop a ball at the same time you're blasting it, and those two balls would have the exact same vertical motion? Bam. Right? You guys said? Right? Now, let's break apart this parabola motion to what's going on horizontally, what's going on vertically. Okay? So if you're up here in a blip and you're watching this thing going across, to you, way up here in a blip, it would look like approximately going constant speed across the field. You see every second. Right? See how it's like equally spaced? You see equally spaced going all the way across? Right? But what if you're like down here and you're watching it come like down like, right? You guys see every second? It's like spreading out. Okay? Who can tell me, maybe I got a really tall cliff here, Okay? How far would it fall during the first second? How many meters? Wait, what? How far to go to the edge of the cliff, drop a ball? How far does it fall in 1 second? Edge of a cliff, drop a ball. How far in 1 second? 5 meters, right? Isn't that the college equation right here? Y equals 1/2 GT squared. You can say H equals 1/2 GT squared. Here, pop in 1 second here. 1 second square, 1 squared is 1. Half of 10 is 5. Okay? It's gonna fall 5 meters in the first second. Right? It'll pick up to 10 meters per second vertically, right? But it fell 5 meters, right? Is that right? How about after 2 seconds? How far did it fall? Yep, 20 meters. After 3 seconds, how far from the 45 meter, right? Right. If it took, looks like it took about 5 seconds to reach the valley floor, how tall is my cliff?
125.
Ha 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 ha. It's about 125 meters. How'd you know that?
Math.
College. And math and physics and the college equation. Oh yeah, college. Oh yeah. You guys remember college? Remember going there? Okay. Yeah. Okay. So now we got x coordinates, we got y coordinates. Put it all together. You can know exactly where on the parabola you're going to be every single second. Okay, you guys got that? Okay. Now, how are we going to figure out blast speed? All right, so here's something that ideally I should just leave this to you to figure out at this point, but I'm going to help you guys out a bit because I got a poster just to answer that question. I'll show you the whole thing, and then see if tomorrow you can pull out a piece of paper and like solve it from scratch yourself. Okay. So here's the equipment we're using tomorrow. This is the cannon. Oh look, it's a projectile launcher. You guys see that? Okay. And I got some balls. So I can put this ball in here. It's gonna launch this thing. Ooh, look. Do you guys see like a spring? Spring? Ooh, this thing's gonna be like spring loaded. And then here's the I can pull the release. It's like spring thing. A few weeks from now, we'll talk about the physics of springs. So that's gonna come back. Talk about Hooke's law and whatnot. Right? But for now, let's compress this thing. Now listen real close. Listen for a click. Guess here, click. Now it's spring loaded. Now it's ready. Okay. Now if I lift this thing, it's gonna fire. But you know what? Listen real close again. Ooh, did you guys hear a second click? Guess hear a third click? Now it's really spring loaded. Oh man, this thing's gonna blast. It's gonna blast so hard. If I put this ball in here, okay, and I pull this, it's gonna fire up. Ooh, I wonder how fast. How fast was that? Oh, let me tell you guys a technical detail. Okay, this will be important for tomorrow. Okay, so for tomorrow, here's what you don't want to do. If you this little squishy bouncy ball, if you put this in first and then you ramrod it, then your whole lab is going to be playing a game of get the squishy ball out of the launcher, which is not as fun as launching them. So see if you guys are following this. What do you want to do first? Do you want to put in the ball first, or do you want to ramrod it first? So you guys are going to ramrod first, right? Ramrod first? Okay, and then put the ball in and then launch it. Aha. Okay, so you guys got that? Okay. But hey, I wonder how you can figure out blast speed. Maybe something to do with like where it lands, right? Okay. So let's look at next poster here. Poster. All right. Oh, hey, look, it's the same thing. It's just shrink. Look at that. Okay. Now there's some things that are really easy to measure with the meter stick. Like I bet you guys can measure the height of the balcony in meters. You guys could do that. Okay. Maybe okay. And then could you guys blast it out and then take a meter stick and say, it's like so many meters out with the meter stick. Okay. Now, if you know the height of the balcony, you know where the ball landed because you just spot it where it landed, how far away it is, okay? And you know you blasted horizontally, right? And you also know Earth's gravity field. Is that enough info where you can, in principle, determine what is the blast speed of that launcher? There must be some particular blast speed that corresponds to exactly where that ball landed. Yeah, I think so, right? So I'll walk you guys through the solution right now. Again, tomorrow, see if you can pull out a piece of paper just blank and solve this from scratch, right? Well, here's what I'm thinking. I know it's going across at constant velocity, constant horizontal velocity. That would be true, right? And that would also represent the blast speed of the cannon because we aimed the cannon straight horizontal. So the blast speed is the horizontal component of velocity, right? You see that's one and the same thing, right? Which is how far it went divided by how much time it took to get there. You see that? The blast speed, the horizontal speed, same thing, would be how far it went divided by how much time, right? The horizontal displacement divided by the time of fall, right? Now, how are we going to get the time of fall? What do you guys think would be more accurate to get the time of fall? To get out there with the stopwatch and be like, or to calculate it based on the fall height? What do you think is more accurate?
Fall height.
Yeah, calculate it based on the fall height, because there's a lot of plus or minus error working with the stopwatch. So we're going to calculate it. A lot more accurate result. Well, how can you figure out how much time based on the fall height? Ooh, does that sound like, you guys remember the reaction time activity last week with the ruler? How'd you guys drop the ruler? This is exactly what you did. You took the college equation, the height it falls is 1/2 gt squared, you scramble around with some algebra, and you get the fall time based on the drop height, right? That's what you did for the reaction time. Right, you guys remember that, right? You guys know what g is on Earth, about 10 meters per second squared. So you pop it in, and then now you got a pretty accurate value for fall time, right? If this balcony were 5 meters up, it would be pretty dang close to 1 second, right? Might be pretty close to what you're looking at, right? And then you can divide these two. Well, I know horizontal displacement went that far in that fall time, and then you can get to blast speed. I guess that. Right? In fact, if you take this entire expression for time and divide it down here, You guys know if you divide by a fraction, just flip and multiply kind of deal. Right? Now, this proof that you guys are looking at right in front of me right now, that actually is right at the level of an AP FRQ question. Like if AP asked this exact question and they just gave you some general drop height, some general horizontal displacement where you can spot the ball, and so some general gravity field and said like solve for the blast speed, like, I could totally see them wanting you to derive this and get like this exact answer. So be ready to field something like that. Right? Be ready to like be at that level. Right? Although you're working in your lab tomorrow and you got just numbers to work with. Oh, I know so many meters up and I got a number here, and you can do it like step by step. You know that too, right? Okay, you guys good there? Okay, let's write an example. An example. So these numbers aren't going to match your numbers tomorrow, but it's a good idea. So, I got a cannon. I got it blasted straight horizontal. Right? And maybe that's my question. It's like, what is the blast speed? What is V blast? Which you guys know is also V sub X. It'd have to be the same thing, right? This thing's going to take off like a parabola motion, right? Follow to a parabola path. Okay? Let's suppose that this cliff is like h equals 45 meters. So 45-meter tall cliff. You guys see 45 meters? And let's also suppose that it lands at a distance or horizontal displacement 120 meters out. Right? Could you guys figure out the blast speed of that cannon with those numbers? Say we're on Earth, right? We're on Earth, right? What's the first thing you would do? Find the time. And which of these, the vertical or horizontal, is going to determine how much time? Vertical, yeah, the height of the cliff. So let's start with vertical info. Maybe I want to use h equals 1/2 gt squared, right? Yeah. Now remember, I can use this simplified expression in one of two cases. Either I just drop the ball or I throw it straight horizontal. Right? Now if you aim it at some angle, then it gets a little bit more complicated. Okay, right, guys got that? Okay. So we're solving for this t. Right? So here, I'll just go ahead and plug in numbers. 45 meters. You should be able to do this in terms of variables, though. Great, AP. Right, 1/2 10 meters per second squared. Time we're solving for squared. Okay. Ooh, guys, what's 45 times 2? 90 divided by 10. Square root. 3 seconds. Right? Or maybe you could have told me that. Maybe you could have said, well, if you're standing on a 45-meter tall cliff and you drop a ball, it's going to take 3 seconds. Because it's the same thing. Could have said that. Okay. Now we're going to switch over horizontal. Horizontal, right? Ooh, should I use V sub X is horizontal displacement divided by the time? Just like that. X over T, right? This distance, this horizontal displacement divided by that time. Does that look like 40 meters per second? That would be the answer, wouldn't it? Is that? Boom, boom, right? So you guys see how these are going to be process questions, right? Process questions, right? So yeah, when you see projectiles, think this is going to be a process. Yeah. Sometimes you start with horizontal information. Sometimes, like this example, you start with vertical information. You see what's going to constrain it. Okay, you guys get that? Right. Follow-up question: what is the crash speed? You guys see the balls coming in, crashing at some angle right there? Is it? I'll call this V crash. Okay. Would the crash speed be faster than the blast speed? Do you guys think?
Yes.
Yeah, true. It is picking up speed. Right?
Because it'd be the magnitude of dx and dy.
Exactly. Yeah. You guys hear Steve? It'd be here. You said exactly what I was thinking next. Right. You want to think about this in terms of components. You want to say, well, this is V sub X. This is I'm going to say V final in the Y direction, right? Because your Vy is always changing, right? So this is V final in the Y. Your Vx is just Vx. That stays the same all the way across. But your Vy, that's changing, right? Right. And Vx we already have a number for, right? Here's your 40 meters per second. Right? But what is V final in the Y direction right at the crash point? How fast is it traveling strictly vertically? Does anybody know? How fast is it traveling vertically after falling for 3 seconds? Go to the edge of the cliff, drop a rock. How fast is it falling after 3 seconds? 30 meters per second. Ah, there you go, right? Or if you like, you can use that third kinematic formula and said, well, if it falls 45 meters, it's also going 30 meters per second. That's the tricky one, like df squared equals v naught squared plus 2ax. But however you do it, yeah, we're talking about this row. Yeah, 30 meters per second. You guys see that? Right? So might do something like v equals gt. Right? Here, let me go ahead and finish this off here. So I got v crash we're solving for. I'm gonna split. Notice I'm dashing my components. You guys see how I'm dashing the components like that? AP is big about that. If you don't dash them, they just don't give you any credit. Right? V sub x we figured out was 40 meters per second. Right? That was a whole process. V final in the y direction is the same thing as g times t. 10 meters per second squared times 3 seconds is one way to get it. 30 meters per second. Bam. Right? 40 meters per second across, 30 meters per second down. What's the total crash speed? Who sees it? Guys, this is a what triangle? Who sees it? Here, how could I find out in general? If you know the two legs of a right triangle. Ah, yeah. You guys hear Reese? 3, 4, 5 right triangle. 3, 4, 5 right triangle. Right. So yeah, there you go. Right, so you do 30 squared plus 40 squared. This is square root of all that. This is some number of meters per second. In this case, yeah, 50 meters per second is the crash speed. Ah, right. So it is picking up speed as it's falling, right? Okay, you guys see that too? Okay, so the cannonball was blasted at 40 meters per second horizontally. So it's horizontally 40 meters per second the entire way. Because the cliff was 45 meters tall, that means it took 3 seconds to fall, and it built up to 30 meters per second in the vertical direction by the time it was just about to hit the ground. Put those two together, well, they're perpendicular, right? The total crash speed, yeah, Pythagorean theorem gives you 50 meters per second. So like the 3, 4, 5 geometry, that's a specific case of Pythagorean theorem, right? Pythagorean triplet, right? Follow-up question, what is this angle right here? Here, lead you guys through it. Getting close on time here. Can I do inverse tan? 40 on 30? It's like 53 degrees, I think. I think it's 53 degrees, right? I'll say from the vertical. I have to specify relative to what that I'm talking about. Okay. All right, guys, see that? All right. One more idea I want to throw at you guys for, yeah, okay, I got just enough time here. Okay. I got one more poster. No, sorry, I have 2 more. They're kind of related though. All right, so suppose we're down on a plane and we're gonna take a cannon and ramp it up some angle, blast a cannonball. You might see a light gray curve. This will be part of a parabola, like it's gonna fall like off paper, right? Right. But maybe I want to know something like here. Maybe I know the blast speed and I know the angle I ramp it up to, and I want to know how far is that cannonball going to go? How far, like downrange? Okay. Now this is going to be a whole process, and the very first step of the process is to break the velocity into components. See how the cannonball is partly going across the field, but also partly going up, right? And this vertical component is always going to change, right? It's going to immediately start slowing down as soon as it goes into free fall. But the horizontal component stays the same all the way across. Right? You guys see it's going to be like a process. Okay? So let's check this out. Get some numbers here. Say we got cannon, I'll blast this at 53 degrees at 100 meters per second. V blast equals 100 meters per second. 100 meters per second. Okay? The first thing I do is I break this into components. Remember the question is, where's this thing going to land? Okay. First thing I do is I break this into components. I say, well, it's partly going across the field. It's partly going up. V sub x. Guys, how do you solve V sub x? That's 100 meters per second times what? What did you do with 53? Sine or cosine? It's adjacent. Cosine. Oh, yeah. Is that going to be 60? No. Hold on. What did I just do?
No.
Yeah, 60 meters per second. Right? Is V not in the Y direction? Look, see a couple subscripts, initial in the Y direction. Is that going to be 100 meters per second times sine of 53 degrees, which is like 80 meters per second? You guys see that? You see that? Okay. Now, after 1 second, how fast is it going strictly up? It changes how much every second, vertically. So 80 minus 10 is 70, right? Isn't it slowing down on the way up? So 70 meters per second, then 60, 50, 40, 30. How many seconds does it take to reach the very top? How many? Guys, if you throw a ball straight up at 80 meters per second, it's losing 10 meters per second every second. It takes 8 seconds. You guys see 8 seconds? From there to there, it takes 8 seconds. Okay. Guys, if it's 8 seconds to reach the very top, guess how many seconds to go back to the ground? Another 8. So what's the total hang time? 16? So if it's going across the field at 60 meters per second times 16, seconds. That could tell you where the ball lands. You guys get that? All right. You guys have a great rest of your day and see you tomorrow. Okay, just for the video, that can also have been answered with the range question. In fact, tell you what, if you're at home, let me show you that. So you guys in class, just go ahead. But just for everybody at home, we show this the same thing. So 60 meters per second times 8 and 8 is 16 seconds. Gives me 960 meters downfield. Yeah, 960 meters downfield. All right. You could also answer that, with this range formula. Oh, let's see, double angle identity. So the blast speed squared divided by the gravity field, all times sine of 2 times the blast angle from the horizontal. Okay. Oh, it's the same thing. Same thing. There we go. Good days.